Hi, I am Shahnaz. In this lecture, we will be doing the coloring of a graph. So let us consider a graph G, possibly finite and simple. Now, by a simple graph, I mean let us consider this graph G, which has vertex set V and edge set E. Now, by simple, I mean a graph. Suppose we have this graph here. Now this graph consists of 4 vertices, say v1, v2, v3 and v4. Now by simple graph I mean a graph with no loops and so by simple I mean which has no loops and no multiple edges. So suppose we have this vertex V. So if we look at this edge over here, this is a loop at V1. By a loop I mean an edge which has both vertices same, and by a parallel edge between two vertices I mean, suppose let us consider these two vertices V2 and V3. Now between V2 and V3 we can draw this edge as well. So if this is edge E1 and this is edge E2, then these two edges E1 and E2, they are what we call parallel edges. So we are considering here a graph which is simple. Now what we are going to do, let's consider this graph over here. So we have this graph with vertex set V and edge set E. Now so this is a vertex set of VG, which consists of these 4 vertices, say V1, V2, V3 and V4. So VG consists of these 4 vertices. Now let us do one thing, let us color each vertex. So let us color each vertex. So we can color these vertices either using one color or 2 colors or possibly 3 colors, but not more than 4 colors because we have just 4 vertices. So let us take this color over here and let us color this vertex with blue color, and let us color this vertex with say magenta color, and V4 will also color this vertex with the same color, and let us color this vertex with V3 with green color. So what we actually did, we are assigning a unique color to each vertex. So for vertex V1, so for vertex V1 we chose the blue color. So this is our vertex V1. So for V1 we chose blue color. For V2 and V3 we have a red color. So this is blue and this is red. And for sorry, not V3, this is V4 here. And for V3 we chose the green color. So we are using these 3 colors to color these vertices over here. So one can choose different colors to do the same job. So one may color vertex V1 with, suppose with gray, suppose V2 with suppose cyan color, and suppose V3 and V4 with black color. So this is another coloring. So for a given graph we may have different colorings, but what we are interested in those colorings such that no two adjacent vertices get the same color. Suppose if we look here, vertex V2 and V4, they are adjacent. So what is the game? The game is that they must get different colors because they are adjacent. So this coloring is not gonna work here. Similarly, if we color V3 and V4, we are taking this black color. This coloring is not gonna work. So what can we do? We have to color this graph such that no two adjacent vertices get the same color. So let us take this coloring. Suppose this is the vertex V1, vertex V2, vertex V3 and V4. So this is V1, this is V2, this is V3, this is V4. So first of all we have to color, we may color any vertex. So let us choose this vertex V1. Let us color this vertex V1 suppose with this color, I mean with blue color. So now this vertex is done. Now we have to look over all those vertices which are adjacent to V1. Now in this case V2 is the only vertex which is adjacent to V1. So V2 must not get the blue color. So let us pick some different color. So let us pick this color, magenta. Now we have to look for the neighbors of V2. Now V2 have got two neighbors, V3 and V4. I mean these are the vertices which are adjacent to it, and sometimes these adjacent vertices are called neighbors as well. So for V3 and V4 we have any choice of colors except this magenta. So we can color V3 with blue as well because this blue already appears here. So we can paint this vertex with this color also because V1 and V3 they are not adjacent. Similarly we can color V4 with blue color also, but let us color this vertex with green color. So this is the coloring which we are interested in. So let us define first what do we mean by coloring. So we have this definition. So a vertex coloring is actually a function from the vertex set Vg to another set, that is a set of colors. So let us consider let G is called V comma E be a graph, which is having vertex at V and edge at E. So a vertex coloring, so our vertex coloring of G is actually a function. So it is actually a function. So this function is going to work like this. So we have this function is from these vertices to this set, color set. So if this is the set Vg, and let us call these colors color 1, color 2, color 3. So this is actually a function from vertex set Vg to the set 1, 2, so on. So if graph is finite, this set the range of this set will be finite, otherwise it is going to be infinite. So our vertex coloring of a graph G is a function, say f, from the vertex set Vg to some set, say 1 2 so on, and this set is called the color set. So we are picking colors from this set to color these vertices of G. So a vertex coloring of G is a function from VG2 such that no two adjacent vertices get the same color, such that no two vertices get the same color. So it is actually a labeling. So what we are doing, we are labeling each vertex with its color. Now let us define what do we mean by a chromatic number. So let us look at this coloring. So this coloring, this is not the coloring we are interested in, because these two adjacent vertices, they get the same color. Now as far as this coloring is concerned, this is the coloring that we are looking at, because if we look at this coloring here, no two adjacent vertices get the same color. Now the question is, we have used here three colors: blue, red and green. Now the question is, can we reduce this coloring? Can we reduce the colors such that suppose we are using here three colors. Now there is a question, can we use just two colors to color these vertices? Now suppose we have taken color blue here. So for this vertex we can color this vertex with any color but the color blue. So that means we cannot use a blue color here. So we as far as this edge is concerned, we have consumed two colors. Now it remains these two vertices. Obviously we can use blue color here, because V3 is not adjacent to V2, sorry, V3 is not adjacent to V1, but it is adjacent to V2, so we cannot use red color here. Now it remains vertex V4. So of course V4 is not adjacent to V1, so we can use blue color, but at the same time V4 is adjacent to V3, so we, and this makes us to use different color from red and blue, so we are forced to choose another color. So these three colors, they are the minimum color minimum number of colors to paint these vertices. So the minimum number of colors required to color the vertices of a graph, that is called the chromatic number. So if we look at this graph here, so we can use a red here, blue here, a red here, suppose green here, and suppose this cyan color here. Now let us look at this graph. So we have used 1 2 3 and 4 colors. So now the question is that whether this graph, suppose is the graph G prime, does it mean this graph G prime has chromatic number 4? Now we have to look again at this coloring and check whether this coloring can be reduced to some smaller number. So as far as this part is concerned, we have consumed three colors here. So I can paint here blue color, so this reduces. So if I paint this vertex with blue color, I'm still good. So now we have consumed just 3 colors, so this is the chromatic number. Now this chromatic number, this number of colors, this cannot get reduced further, so the chromatic number here is 3. Now let us define this number. So this is another definition. So a graph G is said to be K chromatic. So this is called a K chromatic if the minimum number of colors, or let us do this way. So let us do this way. The minimum number of colors, the minimum number of colors, let us say K colors, the minimum number of K colors, the minimum number of K colors required to color the vertices of a graph. Let us get rid of this K here. The minimum number of colors required to color the vertices of a graph such that no two adjacent vertices get the same color, get the same colors is called the chromatic number, is called the chromatic number. Of G. And this chromatic number is sometimes also called as the chromatic index of G. This is called the chromatic number of G and is denoted by this chi of G. That is this chi of G. So this is chi of G. So i.e. this chi of G is defined to be the minimum number of colors required to color the vertices of a graph in this fashion, such that no two adjacent vertices get the same color. So if chi of G is K, then the graph G is called K chromatic number. G is said to be K chromatic. So if chi of G is K, then G is, this follows. This means that if chi of G is K, then G is called K chromatic. Now so sometimes if we just need two colors to paint the vertices of a graph in this fashion. Then that graph is said to be two colorable, and three colorable if we need three colors, and like that. Now one can observe here that, so let us consider a graph G here. So suppose this is the graph. Suppose this is our graph G. So one can note here, if we have to color this graph, so let us start with any vertex. So let us start with this vertex. Let us color this vertex with this color cyan. So now let us look for the vertices which are adjacent to this vertex over here. So let us first call these vertices. This is v1, so this is v1, this is v2, v3, v4, v5, v6 and v7. So what we did, we chose this vertex v2 and we used this color here. Now let us look at the neighbors of vertex v2. So one can see over here that vertices v1, v6 and v3, these are the neighbors of v2. So to color these vertices we can use any color except this cyan color. So let us choose this red color here. Now this v1 has just one neighbor v2, so we need not to worry about this vertex. This vertex is gone. Now let us look at these vertices v3 and v4. Obviously we cannot use color red here because v3 and v6 are not are adjacent. So let us paint this vertex with, say, green color. Now this far we are good. Now vertices v3, v6 and v7, they are all adjacent to each other. So in this region we just need three colors to get consumed. So we can use this color here for v7, I mean the color cyan. We can use this color here. There is no harm in that because v2 and v7, they are not adjacent. Now let us look at v5. So we can use any color here for v5 except the color red, because v5 and v6, they are adjacent. So let us choose the already chosen color. Let us choose the already chosen color. So we can color this vertex with green or cyan but not red. So let us take this color green here. Let us paint this color green here. So let us paint this vertex with green color. Now we are left with vertex v4. So for v4 we cannot use green color, but we can use cyan or red. So let us choose color, say, red here. Now if we look at this vertex set v6, v of g, so v of g, its size is 6 and the chromatic number for g is here. So we have chosen 1, 2, 3 colors. So the chromatic number for g is 3 because we have chosen these 3 colors, red, cyan and green. So chi of g, this is 3. Now what is special about this chromatic number. So if we are given a coloring, each coloring induces a partition on the vertex set. Now what do we mean by a partition? Say suppose we have a set S, and let S1, S2, so on, S, suppose Sm. Suppose these are the subsets of S. Now these subsets S1, S2 through Sm, they are said to form a partition of set S if two conditions, if they satisfy two conditions. Condition first is that they are mutually disjoint, i.e. if I take Si and Sj, where this I is not equal to j, and take their intersection, so it must be an empty set. Now condition second is that if we take union of these sets, so if I take union of these Si's, where this I runs from 1 to n m, so this must be called S. So these two conditions, if they are satisfied, then these subsets of S, they are said to form a partition of S. Now what is our claim here? We are saying that whenever we are given a graph G, and it is, so let us pick our black color. So what is our claim here? So we claim here that if we are given a graph G and a coloring of G, then this coloring induces a partition on the vertex set of G. So here we are given this coloring, so this induces a partition. Now how this induces a partition? Let us look at those vertices of G which get the same color. So as far as color red is concerned, so here three vertices are lying, V1, V4 and V6. So these are the vertices which are painted with red color. Now let us look at the vertices which get the green color. So this is our S1. So green color, so green color is achieved by V3 and V5. So V3 and V5, and finally the cyan color. Now in cyan color we have these two vertices, V2 and V7, V2 and V7. Now if we call this set to be the set S1, this S2 and this S3, so one can observe here that these Si's, they are mutually disjoint. So Si intersection Sj, this is empty for all I not equal to j, where this I and j, this lies between 1 and 3. So this lies between 1 and 3. So this is true for all I not equal to j, where this I and j lies between 1 and 3. And next thing is that if I take this union S1 union S2 union S3, which is same as union I runs from 1 to 3 Si, it is actually Vg. So these Si's, they do form a partition of vertex set Vg. So whenever we are given a coloring, that coloring induces a partition on the vertex set. So let us make this an observation. So let us call this observation 1. So if Now one can note here the chromatic number of G was 3. That is why we got these 3 subsets here. So this is the observation. Suppose chi of G is 3, then V of G, I mean vertex of G, can be, sorry, not 3, let us call this K here. Then Vg can be partitioned into mutually disjoint subsets, say V1, V2 through Vk, such that their union is V of G, such that union I goes from 1 to K of Vi. This is actually Vg. So this was the first observation. Now one can look at here at these sets S1, S2 and S3. Now we call a set of vertices to be independent if no two vertices in that set are adjacent. So if we look at S1, so S1 contains V1, V4 and V6. V1, V4 and V6. So one can look at these 4 vertices. So these 3 vertices, no two vertices among these vertices are adjacent, so they do form an independent set. By independent I mean when the vertices in this set are not adjacent. So this is an independent set, this is an independent set, this is an independent set. So one can add here one more term. So then Vg can be partitioned into mutually disjoint independent sets. Independent subsets. Now, of course, they are the subsets of Vg. And these subsets are called sometimes color classes. These subsets are called the color classes. Color classes. And the function f from vertex at Vg. Now, as already mentioned, a coloring is just a function from a vertex, from the vertex set of Vg to the colors that we have used to color the vertices of the graph. So here chromatic number is k, so we have used k vertices, sorry, k colors. So this coloring, because here this is 3 chromatic, so we have used 3 colors. So this coloring actually is a function from vertex set Vg to this set 1, 2, 3, where we have used these 3 colors, 1 for red, 2 for green and 3 for cyan. So here in this observation, the G is given to be k chromatic, so we have used k colors. So this function Vg from this set having k elements, this is called the color function. Let us do some more observations. So this is observation 1 here. first operation. Let us denote this operation by Roman 2. So there is this question: what is the least number of colors that we are required to color the vertices of a graph? So the least possibility for the number of colors is 1. So if we are given a discrete graph, now by discrete graph I mean a graph having no edges, having just isolated vertices. So if we have this graph G having suppose 3 vertices v1, v2, v3 and having no edge, so to color this graph we just need one color. Say let us color these vertices with red. So there is no harm in that because they are not adjacent, so we can use just one color. Now as long as we have one edge, so if our graph consists of just one edge, so by definition of an edge, it connects two vertices v1, v2. So a graph having at least one edge has chromatic number at least 2. So for a graph G which is having at least one edge, we just need minimum number of 2 colors to paint the vertices of the graph. So in this case we are using blue and red. So a graph G is one chromatic if and only if it is totally disconnected, and a graph having at least one edge is at least 2 chromatic, I mean bichromatic. So a graph G is one chromatic if and only if it is totally disconnected. By this term I mean a graph having no edge. Let us do one more observation. So a graph G having at least one edge is at least 2 chromatic, is at least 2 chromatic. Now what does that mean? i.e. the chi of G is bigger or equal to 2, because at least we are going to need these 2 colors to paint the end vertices of that edge. Now let us look at this graph. Now this is K3, complete graph on 3 vertices. So let us color this vertex with blue color. Now for these 2 colors, these 2 vertices, we have to choose another color different from this blue color. So let us paint this red and paint this vertex with say green color. So for K3 we need 3 colors. Now let us look at K4, I mean a complete graph on 4 vertices. Now let us recall what do we mean by a complete graph. So a graph is complete, a graph on n vertices, complete graph if any 2 distinct vertices are adjacent. I mean if we look for 2 distinct vertices, there must be an edge connecting these 2 vertices. So a complete graph on k n vertices is denoted by kn. So let us look at K4. So this is the graph K4 v1, v2, v3, v4. So there is an edge between any two distinct pair of vertices. So if we look at v1, v2, we have an edge, v2, v3, v1, v4, v1, sorry, so v1, v3 and v2, v3 and v1, v3, and finally from v4, v3. Now let us color this graph. So let us choose a red color here. Now we cannot color this vertex with red color since v1 and v4 are adjacent. So let us color this vertex with cyan color. Now let us paint this vertex. So we cannot use these two colors because v2 is adjacent to both these vertices. So let us choose this green color here. Now we are left with v3. Since v3 is adjacent to v1, v4 and v2, so we have to pick a different color to paint this vertex here. So let us paint this vertex with black color. So for this graph K4, the chromatic number is chromatic number here is K4. For K4 we have 4, and for K3 we have 3. So add the number of colors that we are going to need to paint the vertices of a graph is at most the number of vertices, that is, so let vertex set of G has size n, then the chromatic number of G is less or equal to n. Now less or equal to n. So this is the maximum number of colors that we can use. Let us do one more observation. So let G be a graph and H be its subgraph, then certainly chromatic number of H will be less or equal to chromatic number of G. So if H is a subgraph of G, then this chi of H is less or equal to chi of G. Now let us do one more observation. Now suppose we have a graph G such that it is having k components, or say m components. So this is the graph G which is disconnected and it is having k components, and let us suppose in this case we have 4 components. Suppose we have vertex v1, v2, v3 here, v4, v5, v6, v7, v8, v9, v10. Now suppose this component has 3 vertices, this has 2 vertices, this has 2 vertices, and this has 3 vertices. So the max, let us put one more vertex here, suppose v11. So this is 4, this is 2, this is 2, this is having 3 vertices. Now what is the maximum number of colors that we are going to use to color this graph? So maximum number of colors that we are going to need is 4. So we can use just 4 colors to paint all these vertices. Now one can note here these are this graph is given to be disconnected and having these 4 components. That means no vertex over here is adjacent to any vertex among these components. So suppose if we need three colors here to paint this component, we can use also those three chosen colors to paint this component, and finally this component, and lastly this component. So let us make an observation here. So if G1 so on Gm are the components of a disconnected graph, so this graph is given to be disconnected. Then the chromatic number of G will be the maximum of chromatic number of these individual components. So then chi of G will be equal to maximum of chi of Gi, where this I is lying between M and this is I and 1. So now let us look at the cycles. Suppose we have a 3 cycle here, then a 4 cycle, then a 5 cycle, then 6, now let us color these vertices. So one can see over here every vertex is adjacent to every other vertex, so we just need 3 colors to color this graph. So we can use green, red here and blue here. So the chromatic number is 3. Now let us color this graph. So we can use a red color here, we can use blue here. So we are good at red because we can paint this vertex with red color because these two vertices are not adjacent. Then we can again use blue. So one can look here, this is the coloring, no two adjacent vertices get the same color, so the chromatic number is 2 here. Now let us move to this graph. We can use red here, then blue here and red here, blue here, red here, then again blue. Now we can not use red because if we paint this vertex with red color, that will not be a coloring that we are interested in, so we have to pick a different color. So let us pick the color green. So this is the number, chromatic number will be 3. Now for this graph we can color this vertex with blue, this vertex with blue, and this with blue, and this with red, and red. So the chromatic number will be 2. So one can observe here, if we have odd cycles we need 3 colors because this is the 3 cycle, this is the 5 cycle, we need 3 colors, and for even cycles we just need 2 colors. So let us make this an observation. So this is I guess observation 8th. So a cycle, so for a cycle Cn of length n, so this length is given to be n, comma we have, so chi of Cn this is 2 if n is even and 3 otherwise.